All right, so the last talk of this session is about Snapdoc, a collaborative peer-to-peer editing system, and it will be given by Stefan. Please take it away.
Thank you. So in this research, we consider the problem of collaborative editing, real-time collaborative editing. So, I mean, applications like Google Docs or Office Online, where two or more users want to concurrently edit a shared document. Here, conceptually, this works like every user or device stores a copy of the document, and then any changes are first applied locally and then shared with the other collaborators. So for this real-time editing system, it's important that there should be no merge conflicts that need to be resolved manually, and that all replicas need to converge to the same state in the end. So current popular existing systems for collaborative editing, they all essentially require the user to fully trust the service with all the data. So we wanted to design a system where we have better privacy properties. In particular, we wanted to support end-to-end encryption, and we wanted better metadata privacy. So, for example, being able to hide who collaborates with who. So we went for a peer-to-peer model, which first of all naturally gives better metadata privacy because not everyone's data has to pass through a central point. And secondly, we can also more or less straightforwardly support end-to-end encryption because we can simply pass all the messaging through an existing secure messaging protocol. And additionally, the decentralized model has the advantage that users can now collaborate offline without internet connection as long as they have a local network connection. So if we want to build such a system, first of all, we need some data structures that allow concurrent editing. So for this, most existing systems use something called operational transformation, which relies on a central server to totally order all the edits, and who transforms any concurrent operations so they can apply it in different orders on different devices, which requires access to the plain text. So for these reasons, these systems are not compatible with our privacy goals. But luckily, in the last 10 years, an alternative to OT has become popular and has been researched, which is called CRDTs for conflict-free replicated data types. So these CRDTs are a replicated data type where one can independently perform changes on any replica and then directly share it with any other replica. And the main idea behind those is that all operations are designed to be commutative, so they can be applied in different orders on different replicas to still receive the same outcome. So example of a simple CRDT is TreeDoc, which is also the one we used in our research. Here the document is represented as a binary tree of atoms, where an atom could be a character or a word or a line, for example. And the tree describes the order of these atoms within the document. So essentially like a binary search tree. And the position of each atom in the tree is simply described by the path from the root to the atom. Now we also attach the user ID of the creator and a per user sequence number to each atom. So we get so each atom has a globally unique ID, which we need, for example, so we can refer to it when we want to delete it. So TreeDoc supports two kinds of operation. You can insert or you can delete an atom. But now what happens if two users concurrently add an atom in the same place? So in this case, this gets resolved by basically both of these atoms get added in a so-called major node, and then we still need to make sure that every user ends up with the same ordering of those atoms. So we simply use the user ID of the creator to decide who comes first. So in this example, user A's atoms user A's atom could always come first. So, but now that we are in a decentralized model, we introduce some new challenges because we don't have a trusted server anymore. So in a centralized model, the server can ensure that all users are authenticated, that everybody sees the same document, and he also prevents it prevents users from cheating. So, for example, a user could try to show different versions of the document to different collaborators. So, for example, you could imagine a scenario where you have a real estate agent setting up a contract for selling a house, and then showing slightly different versions of the contract to the buyer and seller with different prices. So they could keep the difference. So basically, a user could try to create a fork of the edit history. Or, like in a decentralized model, if users can forward other people's edit, they could also try to lie about what kind of edits other users have performed. So so that's why we don't want to fully trust all our collaborators. But we still want to aim for similar consistency goal properties as in the centralized model. So in particular, we want to make sure that all honest collaborators converge to the same state. We want to make sure that they can quickly detect any forks in the edit history. And we want all edits to be attributable to their originator. And additionally, we want another property which we call history privacy, which means that when we invite a new collaborator, we only want to show them the latest state of the document, but not any of the history, which might contain some sensitive data or just some unpolished drafts which we don't want to share. So now, if we don't worry about the history privacy for now, how can we get those consistency properties? Well, we just let users sign all their edits, and then we use hash chaining between all the messages, similar to Git. So each message simply refers to the hashes of the latest previous messages. But now, how do we add a new collaborator? What do we send to them? So the first option would be to just send them the full edit history. This way they could verify all the signatures and hashes to make sure their view is consistent with other users. But then this can be expensive if there is a large history, and of course this way we also don't get the history privacy property we want. So instead, we could just send them the latest state, but not any of the history. But then they have no way of verifying the hashes to make sure that they have an authentic state, an authentic view of the document. So what we could do is we could just ask other collaborators then to confirm that they agree with that the state or snapshot that the user has received. But then here the problem is that we need enough users to be online to be able to confirm this, and we also need to assume that a certain proportion of users are trusted. So instead, we went for a different approach, which we call authenticated snapshots, where we again send only the latest state to a new user, but we also attach a proof of consistency, which proves that this state is consistent with the latest views of the other collaborators. This way, we also don't need any minimum number of collaborators to be trusted, because the proof shows that it's consistent with all other collaborators. So how do these authenticated snapshots work? So let's look at an example. Let's say we have 3 collaborators, Alice, Bob, and Charlie. First, Alice writes hello Bob and then goes offline. Then Bob changes it to hello Charlie, goes offline too. And then Charlie changes it to hello Dave and invites Dave as a new collaborator. So now what does Charlie send to Dave? Well, first of all, he sends the current content of the document, or the tree representation, including all the metadata. And additionally, he sends a proof that this is consistent with the latest states of Alice and Bob. So consistent in this case means that basically the state is reachable from the earlier state through a valid sequence of operations. We don't really have time to go into detail here how these proofs work, but to give a very rough idea, it's based on having users always sign their current document state with every message, for which we use reductible signatures based on RSA accumulators. So if you're interested, you can look at the paper for the details. But we are actually not quite done yet, because there are still some ways how users could end up with inconsistent states. The first way this could happen is, so in our example, Alice and Bob haven't actually seen the latest changes that Charlie has made to the document. So Charlie could simply send them a completely different set of changes. So he could essentially fork the edit history between the existing collaborators and the new collaborator. But this will be quickly detected as soon as the 2 groups exchange even just a single message, because each message essentially assigns the state, so they would immediately detect if the signature doesn't match the state they expect. And the other thing that could happen is that, so even so now Dave has received the proof that the state he gets is consistent with both Alice's and Bob's latest state, this doesn't necessarily prove that Alice's and Bob's themselves are consistent. So there could have already been a fork in the history earlier than that. To prevent that, we use Merkle tree consistency proofs. Again, if you're interested, you can look at the paper for more details. So lastly, let's look at the cost of this protocol, because our RSA accumulators are relatively expensive because they use modular exponentiation with large numbers. So we took the edit histories of 270 randomly chosen Wikipedia pages and replayed them against an implementation of our protocol. Then we looked at the computational costs, and we measured about 5 to 6 milliseconds for an insert operation and about 12 milliseconds for a delete operation. So delete operations are a bit more expensive because they also use modular root calculations, which are even more expensive than the exponentiations. So yeah, so this is a little bit expensive if you wanna support per character granularity editing, but it seems reasonable if for other applications where we don't expect such a high frequency of edits. For example, line-based editing or shared to-do lists or calendars. One advantage of using the snapshots is that we don't need to transfer the whole history to the new users. So we also looked at how much data we can save here, and we got an 84% reduction compared to sending the full history. So to summarize, most existing systems, or all the popular existing systems for collaborative editing, rely on a central server while we propose a protocol which is based on a decentralized model, which supports end-to-end encryption, better metadata privacy, and also introduces history privacy through the use of authenticated snapshots. The CPU cost is about in the order of 10 milliseconds per operation, and we achieve a substantial reduction in the amount of data that needs to be transferred to a new user. And lastly, for future research, some interesting directions would be to make the protocol faster, to make it simpler, because actually the protocol is still quite complicated if you look at the details. And also it would be interesting whether one can achieve perfect history privacy, because in our protocol there's still a small amount of metadata that can be that is leaked in a snapshot. For example, through the sequence numbers, you could infer something about how many edits a user has done. Well, thank you, and now I'm happy to take questions.
Hi, thanks for that. So how tied is your protocol to the semantics of the document changes? Because, for example, there are other approaches that rather than having the user ID or something like that resolve the tie, you just maintain kind of 2 copies of that particular segment and then leave that to the users to resolve manually. Is this type of thing something that would be difficult to do with this type of protocol, or is it something that's kind of general enough that you can adapt it to this type of model?
You mean if you want to support manual conflict resolution?
Yes.
Well, then how does a resolution of a conflict work exactly? Would somebody then add another operation to resolve the conflict?
So, for example, you might have so it's like you've got your line of text, and then 2 people edit in the same place, and so what you'll end up with is like a double height line where you've got one person's version of it above and then another person's version below, or like in Google Documents, if you imagine when you're doing this kind of track changes thing where you have a crossed out version and then you have an edited in version, and then this can be resolved to either one or the other by saying accept or reject.
I would need to think about it in more detail, but basically what we need is that the document can be represented as a set of elements, and that you can have two kinds of operation, inserting and deleting to that set. So if you can model it like this, then it should work.
Okay, thank you.
More questions?
Hi, I actually have a question about hash chains. So just help me to understand, what happens if Charlie, for example, receives updates from like Alice and Bob, and produces 2 hash chains where they have different positions. So it's Alice first and Bob next, and then Bob and then Alice, and sends them to them like 2 different versions. How does this conflict get resolved?
You mean if you...
Like Charlie's malicious.
Yeah.
Right, and it produces 2 different views, like 2 hash chains, because you just need to sign. Right, you need to take the last block and you produce something and sign. So what
would be different in these two versions?
I guess order of operations between Alice and Bob.
The order of operations?
Or is it? I guess it's only, yeah.
Well, I'm not entirely sure what you're asking. So are you talking about concurrent operations or just?
Yes. Yeah. So do the hash chains have to be identical at different nodes, or they can be different?
Well, they have to be the same. So there is basically it's not really a chain. It's more like a graph, a directed acyclic graph, where like each edit is basically one node in the graph, and it can point to several previous edits. So, but it doesn't matter in which order they point, because.
Okay, so if they're concurrent, you take the hashes of both. And,
yes.
Okay.
So you need to point to. Well, actually, in our implementation, we point to the latest message from each user.
Further questions? So you mentioning for future research here, and you say make it faster and make it simpler. So what have you already investigated, like how you could do that? Like what are the pieces that could be improved? I guess one is the RSA accumulators, potentially, right? Because you said they are very expensive. So can you like share some thoughts on how you would approach this?
Well, for making it faster, we were thinking about maybe you can use some kind of hierarchical approach or something where you don't always need the per character granularity, but you could sometimes use a larger granularity for a line, and then only sometimes you go down to single characters. This is one thing we were thinking about, but we haven't actually explored any of that.
Okay, yeah, then let's thank Stefan again. Okay.